by now we have many different tests that we can use to test a series for convergence. And at this point in time, we're just going to pause for a moment and summarize and review them all. So here is a list, and then we'll talk about how to choose. So from section 11.2, we actually were able to find the sums of some series exactly. So the first kind was a geometric series. This is a sum from n equals 0 to infinity, a r to the n, and this converges if the absolute value of r is less than 1, and it diverges if the absolute value of r is greater than 1. And if it converges to a over 1 minus r. Note that to do that, your series must begin at n equals 0. Now, a telescoping series, to find the sum of these, you list the nth partial sum, so list Sn, and you should see some kind of cancellation pattern. And that came from the definition of a series, that the sum of a series is equal to the limit as n goes to infinity of its partial sums. Remember that this is adding the first n things. As you take the limit of the number of things you're adding to infinity, that if that sequence converges, that is the sum of your partial sum. And the other test we had was the test for divergence. So what that says is that given a sum of a sub n's, if the limit as n goes to infinity of those a sub n's is not equal to 0, then your sum of a n's diverges. Just as an aside, if the limit as n goes to infinity of a n's is 0, this does absolutely not mean that your series converges. For example, the sum of 1 over n. As n goes to infinity, 1 over n goes to 0, but that series diverges. You should probably always check the test for divergence first in your sort of triage of testing. If the limit of the terms isn't 0, well then you know that the series diverges and you're done. If the limit is 0, you know to look harder and find a different test to apply. The next test we learned was the integral test. And for this, you needed to have a function f of x that is positive, continuous, and decreasing on an interval from 1 to infinity. And also f of n needed to give the a sub nth term in your sequence. And if you have a function that meets these conditions, then the sum of a n from n equals 1 to infinity, and the integral from 1 to infinity of f of x dx, these do the same thing. As in, if the integral converges, the series converges, and if the integral diverges, the series diverges. So when trying to look for a function for which the integral test applies, check and see if your terms correspond to a function that can be integrated easily using like a u substitution or something like that. The next section, we had the comparison tests. So the direct comparison test. So first of all, let's assume we have 0 less than a n less than or equal to b n. So the condition for both of these tests is that the series have positive terms. Okay, so first thing, if you know that your larger series of bn's converge, that implies that the sum of an's also converge. The bigger converges, so must the smaller. Similarly, if your smaller series, an's, diverge, that implies that the sum of your bn's also diverge. So to apply this test, you must find something to compare to, and your inequality symbol must go the correct direction. If you can't establish that, you can't use it. The limit comparison test just requires that you have positive terms, and this says that given two series, so given the sum of an and sum bn, if the limit as n goes to infinity of the ratio of these terms is some number c that's bigger than 0, then the sum of an and sum of bn do the same thing. The next test we have is the alternating series test. This is the first test that we have that accommodates negative terms. So given an alternating series, -1 to the n times some terms bn, if two conditions are met. Condition 1, the limit as n goes to infinity of those bn's is 0. And condition 2, bn plus 1 is less than bn. That's saying that the sequence of bn is decreasing. If those two conditions are met, then the series converges. And the final section, we discussed absolute and conditional convergence. So absolute convergence and convergence. So what this is saying is that if you can establish that the sum of the absolute values converges, that implies that the sum without the absolute values converges. This is how you might deal with series that have negative terms that are not alternating. Note that it is not true that if the sum of an's converge, this does not imply that the sum of the absolute values converge. Okay, the ratio test says that if you take the limit of the ratio of the absolute value of your n plus first to your nth term, and that is less than 1, then your series converges. If that limit is greater than 1, then your series diverges. If the limit is equal to 1, then the test is inconclusive. And the root test is very similar to the ratio test. So first, if the limit as n goes to infinity of the nth root of the absolute value of the nth term is less than 1, then your series converges. If the limit as n goes to infinity of the nth root of your term is greater than 1, then the series diverges. And if it's equal to 1, it's inconclusive. Just a quick note about the ratio and the root test. When I say converges, these both test for absolute convergence. Okay, so this one. So first of all, I don't see any -1 to the n, so it's not the AST. Test for divergence tells me the limit of the terms is 0, so well, we're stuck testing something. And one time the ratio test will always fail is if you have a ratio of polynomials. So the ratio test is no good in this case. Now I would say this looks a lot like 1 over n squared. So we are going to use the limit comparison test. Direct comparison's a bit tricky because you'd have to establish that the inequality, this was always less than something, and that might be a little bit complicated. So we'll take the ANs to be the terms in our series. And the series we're going to compare it to is the ratio of what I would say are the sort of most important terms. So that'd be the ratio of those things, which will be 1 over n squared. All right, so find the limit as n goes to infinity of the ratio of an over bn. All right, and that limit will be 1. And remember here that you need this number that comes out of this limit to be a finite number, so this is bigger than 0. And you can say, well, thus, as the sum from n equals 1 to infinity of 1 over n squared converges, it's a p-series, p equal to 2. The sum from n equals 1 to infinity of n minus 1 over n cubed plus 1 also converges. And let's say why by the limit comparison test. All right, for this one, my first guess is I see this -1 to the n. That to me suggests an alternating series. So we're going to apply the alternating series test. So we try to find the limit as n goes to infinity of 2n squared minus 1 over n squared plus 1. If this series were to converge, this limit would need to be 0. However, it's not. It's 2, which is not equal to 0. Thus, the series diverges by the alternating series test / the test for divergence. Okay, and this one, I see that both the numerator and the denominator have things that are raised to the nth power. So that gives me a hint that I'm probably going to want to try the root test. The ratio test will probably also work, it's just going to be a lot more complicated. So nth root, absolute value, nth term. Okay, the nth root of the absolute value of n to the 2n over 1 plus 2n to the 2n. So the nth root will cancel those nth powers, leaving us just some squareds. So it'll be n squared over 1 plus 2n, the quantity squared. And if I expand that quantity out, that will be n squared over 4n squared plus 4n plus 1. That is 1/4. Since 1/4 is less than 1, the series converges actually even absolutely, by the root test. All right, here you see that the denominator is not raised to an nth power, so the root test no good, but possibly the ratio test will be okay. Let's give that a try. So we're going to find the limit as n goes to infinity, n plus first term over nth term. Okay, when I input n plus 1, I get negative 1 to the n, 5 to the n plus 1, n plus 1 to the fourth, times n to the fourth over negative 1 to the n minus 1, 5 to the n. All right, now here the negative 1s can go away, and once they're gone, we've absolute valued everything. We'll have 5 to the n times 5, n to the fourth, over n plus 1 to the fourth, 5 to the n. Those 5 to the n's cancel, giving us the limit as n goes to infinity, 5 times the quantity, n over n plus 1, all to the fourth. I think that this is easier than expanding, because as n goes to infinity, the limit of this stuff in the parentheses is 1. So this limit will be 5 times 1, or 5. And as 5 is greater than 1, this series diverges. By the ratio test. In many ways, the hardest test to spot is the integral test. I'm pretty sure if you try to apply the ratio test to this expression that it ends up sort of not working very well, and you get that it's inconclusive after much pain. So, but I do know that if I were to like do a u sub for the negative n cubed, that n squared comes in somehow. So this seems like it's a plausible candidate for the integral test. So we're going to let our function f of x equal x squared e to the negative x cubed. And just first note that f of x is positive and continuous. This function is technically continuous and positive everywhere, but we just care about from 1 to infinity. So on 1 to infinity. We need to show that this function is decreasing. To do that, we must take the derivative. So the derivative would be 2x times e to the negative x cubed plus x squared times e to the negative x cubed times negative 3x squared, which is the same thing as e to the negative x cubed times 2x minus 3x to the fourth, or x e to the negative x cubed 2 minus 3x to the third. Now this will be negative if this component is negative, so this is less than 0 if 2 minus 3x to the third is less than 0, which implies that 2 is less than 3x to the third. 2/3 is less than x cubed, or the cube root of 2/3 is less than x. So as long as your x is bigger than that value, your function will be decreasing. So the f is decreasing. Probably that number is less than 1, so on 1 to infinity. Okay, so now that we've checked the conditions have been met, that part's pretty tedious. You have to actually apply the integral test. As in, you must find the integral from 1 to infinity of x squared e to the negative x squared dx, x cubed, excuse me, dx. If this integral converges, your series will also converge, and if the integral diverges, your series will diverge. So first make it the integral from 1 to b, x squared e to the negative x cubed. Let's do a substitution. Let's let u equal negative x cubed. Du would be negative 3x squared dx. If your x is 1, your u is negative 1. And if your x is b, u is negative b cubed. All right, so you have the integral from negative 1 to negative b cubed, negative 1/3 e to the u du. So that will be negative 1/3 e to the negative b cubed minus negative 1/3 e to the negative first. All right, now that first term is the same thing as negative 1/3 e to the b cubed power plus 1/3e. And this first term goes to 0. This integral goes to 1/3e. And thus, the series also converges. As the integral converges, the series must also converge. All right, this, no ratio test. Ratio test will not work with stuff like this, so your options are left to comparison test, integral, and no AST since it's not alternating, so really you're down to comparison. This is an example where direct comparison will actually work quite well, and here's how. So first notice that n times the square root of n cubed plus 5, that's bigger than n times the square root of n cubed, which is the same thing as n times n to the 3/2, or n to the 5/2. So, knowing that, we know that 1/n square root n cubed plus 5 is less than 1/n to the 5/2, and since n is positive, this is also bigger than 0. And as the sum from n equals 1 to infinity, 1/n to the 5/2 converges. Note it's a p-series with p equal to 5/2. Then you know that the sum from n equals 1 to infinity, 1/n square root n cubed plus 5 also converges. All right, here, direct comparison might be a bit more tricky, so we are going to try limit comparison. Okay, so let's let an be the terms of the series. And bn we find by taking the sort of most important terms, n cubed over the square root of n to the 8th, which will be n cubed over n to the 4th, or 1/n. All right, find the limit as n goes to infinity of the ratio of an to bn. If this limit is a finite number that is bigger than 0, we know that both of these series an and the sum of bn's will do the same thing. Okay, an is big old complicated mess. Multiplied by n/1. That makes the limit as n goes to infinity, n to the 4th plus n over the square root of n to the 8th plus 1. Now technically, to find the value of this limit, at this stage we multiply by 1 over n to the 4th in the numerator and denominator. In the numerator, that's pretty easy. We just get the limit as n goes to infinity of 1 plus 1 over n cubed. Now in the denominator, when that 1 over n to the 4th goes into the square root, it must be squared, and 1 over n to the 4th squared is 1 over n to the 8th. So that makes this term a 1, and that a plus 1 over n to the 8. And now you can conclude that as n goes to infinity, this limit goes to 1, and that number is bigger than 0. Thus, as the sum of from n equals 1 to infinity of Bn diverges, remember that's the harmonic series, the sum from n equals 1 to infinity of the ANs also diverges. If you do use this shortcut notation, make sure that you actually give it a summation symbol, because if you don't, you're talking about a sequence and not a series, and the conclusion is different. So you have to make sure that you put a summation symbol if you think you're talking about a sum. All right, negative 1 to the n over root n minus 1. Well, this seems like a pretty straightforward alternating series test, since I have this whole negative 1 to the n and 1 over root n minus 1. So let's let b sub n be the components that are not negative. Okay, we're going to apply the alternating series test. So the first thing you have to check is, what is the limit as n goes to infinity of those bn's? Well, since you only have a variable in the denominator and root n keeps getting larger as n goes to infinity, 1 over big number goes to 0. And then also you must establish that you have something decreasing. Well, bn plus 1 needs to be less than bn. So you notice that, well, root n plus 1 minus 1, that's bigger than root n minus 1. But when you reciprocate 1 over root n plus 1 minus 1, that's less than 1 over root n minus 1. And that's the n plus first term is less than the nth term. And thus, the series converges by the alternating series test. All right, next we have the sum from n equals 1 to infinity of cosine of 2n over 1 plus 4 to the n. This looks a lot like a geometric series, but we can't use the alternating series test because the cosine of 2n term doesn't exactly flip-flop. So what we're going to use here is the fact that absolute convergence, that's going to imply convergence. So the thing that you notice here also involves a little bit of direct comparison. The absolute value of cosine of 2n over 1 plus 4 to the n, that's less than or equal to 1 over 1 plus 4 to the n. That's true because cosine is in between negative 1 and 1, so its absolute value is less than or equal to 1, and this denominator is actually always positive. Now this is also less than 1 over 4 to the n. If you decrease the numerator, you increase the size of that ratio. And as the sum from n equals 1 to infinity of 1 over 4 to the n is a convergent geometric series with r equal to 1/4, the sum from n equals 1 to infinity of cosine of 2n over 1 plus 4n is absolutely convergent and therefore convergent by the direct comparison test. Okay, just a couple more. So test this series for convergence or divergence. So in general, the ratio test and root test ends up being students' favorites because they end up being pretty easy to apply. They work best when you have powers and when you have factorials. So here you've got powers, but this whole little n term means that the root test probably isn't a good idea. So here we're going to try the ratio test. So that tells when the limit as n goes to infinity of the ratio of the n plus first term over the nth term. So plugging in n plus 1, we have n plus 1 times 3 to the 2 times n plus 1 over 10 to the n plus 1 or n plus 2 times 10 to the n plus 1 over n 3 to the 2n. And then a whole bunch of exponent stuff to simplify. We have n plus 1, 3 to the 2n times 3 to the second, 10 to the n times 10 over 10 to the n times 10 squared, n 3 to the 2n. And a whole lots of stuff will cancel. 3 to the 2n's, the 10 to the n's, and one of these 10's. So what we're left with now is the limit as n goes to infinity. 9 times n plus 1 over 10n. And lo and behold, that limit is 9/10. It just squeaked in under 1. And thus the series we have, so thus the series converges, and it even converges absolutely. All right, here, notice we have this thing to the nth power. Well, that's a pretty big hint that you're probably going to apply the root test. So we'll find the limit as n goes to infinity, nth root, absolute value, a sub n. So that's the limit as n goes to infinity, nth root, absolute value, negative 5n over 2n plus 1, all to the nth. Well, nth root and nth power can cancel out. We get the absolute value of negative 5n over 2n plus 1. Now we can move the limit inside the absolute value. We get the absolute value of negative 5/2, which is 5/2, which is greater than 1. And as that limit is greater than 1, the series diverges. So hopefully that summary will help you keep some of these tests straight. And the later lessons that we'll do this week, we're going to also just discuss why these series are useful and discuss some applications.